Welcome Algebra 2 students to our final session of notes for Unit 1, Section 1.8 on special types of factoring. Once again, this is Mrs. Lasner and I will be walking through this outline with you. So in our last outline, you guys learned how to factor a trinomial that looks something like this using a grouping method. And that would also work on this first set of trinomials, that process you learned in the last video. The reason why we're showing you this method, which is it only works on special types of trinomials. In this case, we're talking about perfect squares, is because it can save you a lot of time if you can recognize the type it is. So it's worth your while to memorize these formulas right here. These are the formulas for factoring a perfect square trinomial. I would recommend making some flashcards that have these formulas on them and memorizing them, because the more you memorize them, the more you begin to recognize their structure and setup, and then you might be able to recognize it in one of these examples that I'm going to do in a moment. So before I use this formula, I want you to observe where the formula came from. It came from recognizing what happens when you take a binomial, like for example 3x plus 7, and square it. What happens when you square a binomial, which would be considered a perfect square binomial, binomial squared, something like that. So let's take 3x plus 7 and FOIL it to itself. So squaring a binomial means you write it twice and FOIL. So we do first to first, so 3x times 3x, and we get 9x squared. And then 3x to 7, we get 21x. And then notice that happens again. 3x multiplies to 7, you get 21x. And then 7 multiplies to 7, so basically it squares, and you get 49. Notice that in the middle, we had two terms that were identical. Two identical products of 3x times 7. And then those like terms will add up, and we will have a final result of 9x squared plus 42x plus 49. So let's look at the 9x squared. The 9x squared was what we got when we multiplied 3x to itself. So essentially it's what you get when you square 3x, because I multiplied 3x to itself. And then if we look at the 49, that was what I got when I squared the 7. When I multiplied the 7 to itself, became 49. And then if you look at the 42, that came from adding together these two identical middle terms. So there were two identical middle terms of 3x and 7. So time and time again, after foiling these binomials, a pattern began to emerge, which gave rise to these formulas. And that is that when you square a binomial, the first term of the result is just the square of the first term in the binomial, which we call a. In this case, a that they're talking about in this formula is 3x in this example. And the very last term always ends up being the second term from the binomial squared. So that's what the b is over here. So the first term always ends up being a squared, and the last term always ends up being b squared, because you do end up multiplying 3x to itself when you're doing the f part of FOIL, and you end up multiplying the 7 to itself when you do the L part of FOIL. And then the O and I, the outer product and the inner product, end up being identical. They were both 21x because they were both 3x times 7, 3x times 7. So I ended up with two products of a times b. And so that's what this part right here is, the 2ab. So why are we showing you this? It's because if you can look at a trinomial, like in 1, 2, 3, or 4, if you can look at things like these and recognize, hey, look, it's in this format. This looks like a perfect square trinomial because the first term is a perfect square, the last term is a perfect square, And the middle term is 2 times each of their square roots, a and b. If you can recognize that, then you can use this formula and you're done factoring. You don't have to go through the grouping process. But it does require you to have a good command of what all the perfect squares are and be able to recognize them. So let's jot them out really quick here. I'm filling out the ones that we all know very well. I feel like the squares from 1 to 100 are fairly well known. Once we start going from 11 to 20, I'm going to have to punch some of these in my calculator. I know 11 squared is 121, 12 squared is 144, 13 squared, I always have to check that one. Yep, that one's 169. 14 squared is 196. 15 squared is 225. 16 squared is 256. 17 squared is 289. 18 squared is 324. 19 squared is 361. And 20 squared is 400, because 2 squared is 4, and then 0, the 0 goes from 1 to 2. Okay, so the more you recognize these numbers as perfect squares, the easier it will be to recognize a trinomial as a perfect square trinomial. So let's look at example 1. In example 1, you might notice the first term has a perfect square, right? It has 4. The last term is also a perfect square. It's 11 squared. So far, this looks like it's following the second formula. The second formula, by the way, was found the same way that the first one was. It's if the binomial that's being FOILed is being subtracted versus added. Okay, so when you notice that your second term is negative, which it is in this case, then if it is a perfect square, the factors will each be subtracting a minus b squared instead of a plus b squared. Okay, so what we do is we first look at those terms and we go, okay, the first term is a square of 2x and the last term is a square of 11. So you start with that and then you check. You check the middle term and you ask yourself, is that 2 times a times b, question mark. So in this case, that would be 2 times 2x times 11. And yes, that is 2 times 2 is 4, times 11 is 44, and then x. So yes, if the middle term is in fact 2 times the square root of the first times the square root of the last, this is a perfect square trinomial. You just have to recognize, though, that it's a minus 1, so it's going to use this version, the a minus b squared. We already decided a was 2x, b was 11. So the answer for this is 2x minus 11 squared. Or you can write that out as 2x minus 11 times itself. And that's the answer. And notice I didn't have to do the whole grouping process here because this was a special scenario, right? It wasn't like the typical scenario. The first and last terms were both perfect squares, and the middle term was 2 times each of their square roots. That only happens if I multiply the same binomial to itself. So why don't you guys try number 2? Okay, so for number 2, the answer turns out to be 9x plus 1 quantity squared. Or you can write each binomial out separately. And that's because 81 is a perfect square of 9. 1 is a perfect square of itself, 1 times 1. And 18 is what you get if you do 2 times 9x times 1, which means this particular trinomial is special. And when you do factor it, even if you were to factor it out the long way that you learned in our last video, it would still come out to this answer. So being able to recognize that it's a perfect square trinomial can save you time and energy. Now in example 3, it might throw you off at first because it has both a variable a and a variable b. But don't let that scare you too much because you might notice that they're both squared. I've got a squared in the first one and b squared in the first one. So in this case, a is a from the formula because the first term is a squared. And the last term, by the way, also has a 169. We saw that over here was the perfect square of 13. So it's a perfect square. So I can start by saying, well, b in this case, I'm talking about b from the formula, would be 13b, right? Because 169b squared is what you'd get if you squared 13b. So then when we check to see if this is a perfect square, we're going to see if 2 times a times 13b gives us the middle term that this trinomial had. And it does, because I get 2 times 13, which is 26, and a times b, which is ab. That's why we have an ab in the middle there. Now it is a minus. It is a minus, so that means, so this worked, but that means that when I write my factors out, it's going to be a minus 13b squared would be the answer for this one. Now, because this one was a little different, it had the two variables, I just want us to check by FOILing out the answer. Let's FOIL out the answer and see what happens when I multiply a minus 13b to itself. Because I'm saying that these are the factors of this trinomial. That means when I multiply them out, when I do actually square this and FOIL it out, it should equal the original problem. If it doesn't, then my answer is wrong. So I'm going to start by doing a times a, which is a squared, a times negative 13b, which is negative 13ab, and then again I have the same product, another negative 13ab, and then negative 13 times negative 13 would turn positive. I'm squaring 13, so that's 169, and I'm squaring b, so b squared. Now when I combine those middle terms, I do in fact get a negative 26ab, and I did have an a squared in the beginning and a 169b squared at the end, so it looks like that answer here was correct. So you can always check your factoring answers by multiplying them out, FOILing them out, and seeing if they give you the original problem. Why don't you guys go ahead and try number 4? Okay, so in number 4, if you look at the first term, we see that it's the square of 2x. If we look at the last term, we see it's the square of 5. So then we check the middle term to see if it's 2 times a times b, or 2 times 2x times 5, which it is, because 2 times 2 is 4, times 5 is 20, and there's an x. So it works. So then that means this is a perfect square. It's not like your typical trinomial. It's special and can be factored using this formula right here, ax plus b squared, or you can write each term out twice. The other type of special scenario is called a difference of two squares, because it will look something like this. It's the scenario where the middle term is missing. So this is the formula, which again, like the other one, I suggest that you make flashcards and memorize, because the more you spend time memorizing these formulas, the easier it is to recognize when you have all these problems thrown together. See, right now you might think, oh, this is easy because we're doing 4 in a row. But when I start mixing this together with other types of problems, you may not even recognize what it is unless you've spent some time memorizing this formula. Then it becomes a little bit more obvious what it is. But to see how we got the formula, we're going to go ahead and FOIL something that would be considered the factors of a difference of squares. So notice these factors here. Same terms, 3x and 7, 3x and 7, but one is adding and one is subtracting. Okay, so this is what we call conjugate pairs. Okay, and when you FOIL them, something very unique happens. So let's observe what happens. So when we FOIL, we basically distribute twice. The 3x gets multiplied to the 3x. I get 9x squared. And then 3x times negative 7 gives me negative 21x. And then positive 7 times 3x gives me positive 21x. And 7 times negative 7 will give me negative 49. So then when I go to combine the middle terms, I notice they're identical again. They're both 21 because I had to multiply 3 times 7 twice. But the first time I multiplied it, it was 3 times negative 7. And then the second time I multiplied it, it was 3 times positive 7. So the the terms ended up with opposite signs, and so when you add them together, they add to 0. These will cancel out and equal 0. So the middle term that normally is there and has the x is missing from all of these. This one doesn't have an x, that one doesn't have an m, this one doesn't have a y, and that one doesn't have an x. It's missing. And what we're left with is just perfect squares. The first term was 9x squared. Also, we're left with a subtraction. So it's 9x squared minus 49. Where did the 9x squared come from? It came from this first term, which we'll call a squared. Where did the 49 come from? It came from the second term, b, we'll call the 7b, squared. Where did the subtraction come from? It came from the fact that when I multiplied the L, right, the last terms, positive 7 times negative 7, I was multiplying a positive to a negative. So I multiplied positive 7 to negative 7 because these terms had the same number but a different middle sign. So when you multiply the last terms, you're always going to get a negative. So that's why we call it a difference, right? Difference means I'm subtracting. What am I subtracting? 2 perfect squares. What were they the perfect squares of? They were the perfect squares of 3 and 7, the first and second term from the binomial. So that's what a and b are talking about here, right? If you have something that is a squared minus b squared, which this is, 3x squared minus 7 squared, then when you factor it, it's going to be the square root of the first one plus the square root of the second times the square root of the first one minus the square root of the second. We know that just from observing what happens when I multiply what we call conjugate pairs. The same terms but opposite signs in the middle. So then I look at numbers like 5, 6, 7, 8, and I recognize they're all perfect squares. Look at all these numbers. 36, that's a perfect square of 6, right? So this is 6x squared. 49 is the perfect square of 7. So this is a difference of 2 perfect squares. I can say that the a is 6x and the b is 7. This would be ax squared minus, a squared minus b squared. This is in this format. So then its factors will be in this format, a plus b, a minus b. So that will be my answer. 6x plus 7 times 6x minus 7. One is positive, one is negative. Each one of them are square roots, right? Square root of 36, square root of 49. 6 is a little bit different because the m is not squared, it's to the 6th power. But the 6th power itself is a perfect square. I can think of this as 9m cubed squared. And just as a quick little side note, if I multiply m cubed times itself, which is what it means to square something, you multiply it to itself, I add those powers. Okay, when you multiply same bases, you add the powers. So m to the 3rd squared, meaning multiplied to itself, equals m to the 6th. So m to the 3rd is the square root of m to the 6th. Okay, so I can still think of this as a perfect square. And then 64 is, of course, 8 squared. So this, again, is a difference of 2 terms squared. A would be 9m cubed, and b would be 8. Okay, so then, since there's a subtraction in the middle, and the first term is a perfect square, and the second term is a perfect square, it's in this format. It's a squared minus b squared. So its factors will be a plus b, 9m cubed plus 8, times a minus b, 9m cubed minus 8. Okay, in number 7, it's the same scenario as number 6. I have perfect squares. 16 is the perfect square of 4, and x squared is the perfect, x to the 4th is the perfect square of x squared. So 16x to the 4th is what you get if you square 4x squared. And then 1 is the square of itself. 1 squared is 1. So this again is a difference of 2 squares. where a would be 4x squared and b would be 1. So because it's a difference of squares, I can factor it like this: 4x squared plus 1, 4x squared minus 1. Now just look at this for a moment. Look at this answer. Specifically look at this part of the answer. Does anything strike you about this one? Well, I hope you're noticing, like, wait a minute, 4x squared, that's a perfect square of 2x. And again, 1 is a perfect square of itself. This is another difference of squares hiding inside the answer, so I need to keep going. I'm not done yet. I still have my 4x squared plus 1 factor, but now the 4x squared minus 1 would break into 2x plus 1 and 2x minus 1. Now I'm done. Now I'm done. So you have to always look out for a hidden second difference of squares. Now you guys try number 8. Okay, so in this one, hopefully you notice that the 100y squared is just the square of 10y, and 9 is the square of 3. So this is, again, a difference of 2 perfect squares, so then the factors would be 10y plus 3 and 10y minus 3. And I meant to say this earlier but forgot, but it does not matter what order you write this in. So you're also welcome to write this as 10y minus 3 times 10y plus 3. And the same goes for all of these. So the order of multiplication does not matter. Now another special type of polynomial. Now these special types are not quadratic. They're not to the second power. They are cubes. They are to the third power. But there is a special formula that helps us factor them. So we are able to factor things that are even to the third power now that we're in Algebra 2. So like with the other ones, I recommend that you memorize these formulas. Memorize them. Make some flashcards and study them. Because if you do that, you will start to recognize them. It's all about recognition. If you can recognize something as a sum or difference of cubes, you're halfway there. The second part, obviously, is then to just remember the formula for it. Okay, so if you have 2 perfect cubes that you are either adding, which is a sum, or subtracting, which is a difference, you end up with these 2 factors. One of them has 2 terms, and the other one has 3. So always remember that. It's one binomial and one trinomial. And the trinomial can never be factored any further. So once you get these 2 factors, you're done. Okay? Now, for the trinomial, you might notice the first sign is always opposite the sign from the binomial. So we kind of have a little acronym that goes with this. So we say the first sign, the one from the binomial, is always the same as the original problem. The next sign, which is the first sign in the trinomial, is always opposite the sign from the binomial. And the third sign in both of them is always positive. So we can think of this as SOAP. Same, because that matches the first sign. Opposite, because it's always opposite. Always positive. Notice this, it happens here too. The same sign in this case was negative because the very first, the problem itself had a subtraction. So then the first factor will also have a subtraction. And now the middle sign is positive because it's opposite that first sign. And then the last sign is always positive. So again, you see SOAP in action. Minus, plus, plus. So from there, you just have to remember the order. AB, A squared, AB, B squared. It's the same over here. AB, A squared, AB, B squared. Now, The next and probably the hardest part is recognition. Looking at numbers like 13, 14, 15, 16 and recognizing that they are sums or differences of cubes. So it helps if we first recognize some cubes. So 1 cubed, which of course is 1 times 1 times 1 is equal to 1. 2 cubed would be 2 times 2 times 2 is 8. 3 cubed, which is 3 times 3 times 3 is 27. 4 cubed is 64. 5 cubed is 125. And 6 cubed is 216. 7 cubed, 343. 8 cubed, 512. 9 cubed, 729. And then 10 cubed is a 1 with 3 zeros. Cube tells you how many zeros you'll have after the 1. So it's 1,000. So getting to know these numbers as perfect cubes, 64 of course is also a perfect square of 8 and 8. But it's also a cube of 4, 4, and 4. So that's a really special number. And then these other ones here. So when you begin to see stuff like 512, you might go, oh, wait a minute. That's 8 cubed. But it's all about recognition. And then, of course, x cubed is x cubed. And then they're being added. So this is a sum of cubes. So it's going to use this formula here with the SOAP. A plus b, a squared minus ab plus b squared. A in this case would be the x. B in this case would be 8. So a and b are always the cube roots of a cubed and b cubed. And then I just plug them into the formula. So here it would be x plus 8. The first sign will match. This is a sum, so the binomial will be a sum. Then I square x. Then this sign is opposite. And I just multiply 8 and x. The last sign is always positive, and I square 8. And that's my answer for number 13. So why don't you guys try number 14? So in 14, hopefully you recognize that the 125 is a perfect cube of 5. The 64 is a perfect cube of 4. And so this is a difference of cubes and follows the difference of cubes formula given here. So it'll go into a minus b, and then the second one will be a squared plus ab plus b squared. A in this case is 5x, b in this case is 4. And so plugging those in would be 5x. Whoops, I just noticed I made a mistake. The first term should be 5x minus 4 because it should be the same sign as this. So 5x minus 4 for the first term, the a minus b, and then I have to square a, so I have to square 5x, which is 25x squared. I have to multiply a and b together, so 5x times 4 would be 20x. And then I have to square b, which is 4 squared, which is 16. So this should be your final answer here. Now in number 15, you might be thinking, well, 2 is not a perfect cube and neither is 54, and you'd be right. But I wonder if you would notice that they each have a common factor of 2. So we have a GCF in this case of 2, and I need to factor that out first. So I'm going to take out my GCF. And the first term would just be x cubed, and then the second term would be 27, because I divide 54 by 2. Now I wonder if you notice that the first term now is a perfect cube of x, and the second term is now a perfect cube of 3. Over here we saw 3 times 3 times 3 was 27. So the 2 is still there. I'm going to need to leave it there, but I do now have a difference of cubes remaining, and need to factor that using the difference of cubes formula, where a in this case is x and b is 3, and it's a difference. So using the difference of squares formula, I'm going to do a minus b, so x minus 3, and then a squared plus, because that sign is always opposite the first sign, a times b, which would just be 3x, and then plus, because the last sign is always positive, b squared, which is 9. So my final answer is 2 times x minus 3 times x squared plus 3x plus 9. Why don't you guys go ahead and try 16? So in 16, hopefully you recognize a was 2x, because 8x cubed is the cube of 2x. B was 9, because 729 is 9 cubed. We saw that in our table. So, and they're being added. So this is a sum of cubes. And here's the formula for factoring that. A plus b times a squared minus ab plus b squared. A plus b is just 2x plus 9. A squared is 2x squared, which is 4x squared. And then here I thought I'd write out what a times b looks like. 2x times 9 gives me 18 eventually. And it's minus because it's always, or because it's opposite. And the 89 I got from squaring b, squaring 9. And so my final answer is 2x plus 9 times 4x squared minus 18x plus 81. Lastly, in this video, we'll end by showing you some examples where you might have to do more work than what initially it seems like. In number 17, we've got 4 terms. 1, 2, 3, 4. And normally with a problem like this, we start by factoring by grouping. But what I would like you to recognize is that this one has a GCF, and we should always begin by factoring that out. So always be on the lookout for GCFs. I say this because it will make your life so much easier if you factor them out first. So I notice, okay, they all have an x, so I'm going to take out the x, and I'll be left with x cubed plus 11x squared minus 4x minus 44. So I'm left with that. Now it's a 4 term. So the way we factor a 4 term is by grouping. And what I do when I have 4 terms where the middle one, or the third one I should say, is negative, is I think of that as plus, or plus minus, plus negative 4x. Let me erase this plus sign. Because I want it to be clear that I'm still adding these terms. These terms are all being added, not multiplied. And when we write parentheses next to each other without a sign in between, it implies multiplication. That can get confusing. So these are not being multiplied, these are being added. It's just that that term was negative. Now we look at the first pair and we look at whatever they have in common. So I can see they have x squared in common, so I'm going to factor that out. Meanwhile, this original GCF is still there. So in here, I'm going to take out an x squared, and I'm left with x plus 11. From here, I'm going to recognize they both have a negative in common, so I will take out a negative from both of these, and a 4. And that'll turn this into positive x, and that'll turn negative 44 into positive 11, because if you divide a negative by another negative, it turns positive. So really quick, what happened here is I was doing negative 44 divided by negative 4, which equals positive 11, because the negatives cancel out. When you're factoring, you're basically dividing. So that's kind of what happened there. Okay. So then we notice that we have 2 identical binomial factors. And these identical binomial factors can be considered our new GCF. And I can factor the binomial out. So I still have my x out here. In this problem, I'm going to go ahead and factor out the x plus 11 from this one and that one. And then I'm left with x squared and minus 4. So far I have x times x plus 11 times x squared minus 4. That was a lot of work. A lot of work. But I'm not done yet. Because that sneaky little difference of squares, look at this. This is a they're so small they look like they're done. This is a difference of squares. I have x squared and 2 squared. And they're being subtracted. That's a difference of squares. That will factor into x plus 2 and x minus 2. So this final answer would be x, like from here, x plus 11 from factoring by grouping, and now x plus 2 and x minus 2. So always make sure you factor completely. Okay, last but so not least, you're going to be so mad that we even put this problem on here. But it looks so innocent too. That's the thing with some of these. They're so deceptively innocent. We notice, okay, it's a difference of squares because m to the 6th, I can think of that as m to the 3rd squared. And 64, I can think of that as 8 squared. So I have m to the 3rd as a and 8 as b. So when I begin my difference of squares, so this is going to factor, by the way, into a plus b, a minus b. So m cubed plus 8 and n cubed minus 8. Those are my two difference of squares, right? A plus b, a minus b. Now, I don't know if you're noticing this, but I now have a sum of cubes and a difference of cubes. So you're probably so mad at us right now, like, why, Ms. Lasner, why would you do that? Just, just because I'm doing it with you. It's not like I'm making you do it by yourself. But this is a sum of m cubed and 2 cubed. And then this one is a difference of m cubed and 2 cubed. So it's a sum of cubes and a difference of cubes, both of which need to get factored further. So using the a plus b, a squared minus ab plus b squared, and then this one, a minus b times a squared plus ab plus b squared. So we'll do both of those now. So this one, a is m, b is 2. I'm going to move this out of the way so we can kind of follow better. Okay, so now I have m plus 2 times m squared minus 2m plus 4. That's from this first one, but I still have to keep going. Now I have m minus 2, and then I have m squared plus 2m plus 4. So I had 4 total factors in my answer. And let me just write it one more time because I like to put the binomial ones in front. So I have m plus 2, m minus 2, and then I have m squared minus 2m plus 4, m squared plus 2m plus 4, and that is our final answer. Thanks for staying tuned to this video. I will see you in class.